Okay, so we continue our discussion on decision making. So, when we make a decision, there may be more than one variable which is responsible for it, not just one variable. And that's where you need to work on multi-attribute utility functions. So, when you decide what levels of harmful emissions to allow from a power plant, policymakers must weigh the prevention of death and disability against the benefit of the power and the economic burden of mitigating the emissions. So all the various variables which affect will need to be taken into account, right? And you have a utility function with a number of different attributes. Uh, so when you have more than two attributes, you call it a multi-attribute utility theory. So suppose we have attribute x, which will consist of x1 to xn. So we have n attributes. Okay, and this each of these xi could be either a numerical value or a discrete value, and there will be some ordering on them x1 to xn. So we say x1 is one variable, x2 is the next variable, etc. So higher value of the attribute correspond to higher utilities basically. So if we say absence of noise, the higher it is, the better is the solution. Okay, so let us see how we can keep all these attributes and then decide what is to be done. So first thing, first thing is we look at suppose we are finding an airport site. You have S1 and S2, two sites which are possible, and airport site S1 costs less and generates less noise pollution and is safer and than site 2. Okay, so in other words, in all the different variables that you are talking about, site S1 is better than site S2. So obviously we can reject S2. So we can say that S1 has strict dominance over S2. So whenever you have such a scenario where one uh, value has got strict dominance over the other, then there's no problem in choosing which is the option that you need to take. So when strict domination is there, it becomes easy to narrow down the field. So usually what happens is you may have a lot more choices which are available, but to bring down the choices to just a few, you can use this strict dominance and remove some of those different choices which are available. So, if we take this over here, we can say that A has is strictly dominated by B. So in other words, in all ways, if you take attribute x1 or attribute x2, you can say B dominates A, but at the same time, you can't say that about C and D. Okay. Then you come to another aspect which is called the stochastic dominance. Okay, so it's not as easy as the strict dominance. So suppose we look at this cost of siting the airport as S1 is uniformly distributed between 2.8 billion and 4.8 billion, and the cost at S2 is uniformly distributed between 3 billion and 5.2 billion. Okay. So you find this is what is given over here, right? So we can say that in such a case that S1 stochastically dominates S2 basically, okay, which means that you are taking all the values at different costs and probabilities into account, okay, and you can say that it stochastically dominates. So this is the second type of dominance that you can use. So in this way also you can prefer S1 over S2 because it stochastically dominates the other one, okay. So if we take phi b, right, so here you are examining the cumulative distributions. So what you do, you find the cumulative distribution for S1, okay. So you take the probability of x1 if you have two actions A1 and E2 which lead to probability distributions P1x and P2x, right. Then what you do is you integrate for x between minus infinity to x to get the cumulative distribution. Okay, similarly you get the cumulative distribution for this, right. So then you choose the one which dominates, right. So then you say it stochastically dominates A2. So what you are doing is that you are trying to find it's something like trying to find the area under the curve in some way, right? And then you are saying that this is stochastically dominates the other one, okay? So if A1 stochastically dominates A2, then for any monotonically non-decreasing utility function Ux, the expected utility of A1 is at least as high as the expected utility of A2. Okay, so the expected utility is what you need to take into account basically. So even though you may not know some of the variables properly, or you may not you may not decide it so easily, there are some places where it can be decided easily. For example, suppose that the construction transportation cost depends on the distance to the supplier. The cost itself is uncertain, but the greater the distance, the greater the cost. So it's something like saying that you have the preference between this and this, even though you can't plug it down and say this is the cost basically, okay. So if S1 is closer than S2, then S1 will dominate S2 in cost. So these are all cases where it's possible to separate S1 and S2, okay. So first we spoke about strict dominance, then we spoke about stochastic dominance, and then the third thing where we are able to qualitatively say, right, that this is better than this without going into any numerical values. Okay, then we need to see the preference structure. So suppose all these things are not there, we need to take all the attributes into account. Then you need to have some way of combining the attributes. So you have some function here which combines the attributes x1 to xn, right. So the worst case is there is no agent's preferences have no regularity at all. So you don't know how you can choose, right. So then you use what is called the multi-attribute utility theory. So what you do is that the utility of x1 to xn, find a simple function f, okay, which combines these f1 to fn. So it could be something like addition or multiplication or some very simple function. So first of all you need to check if the values are independent of each other, because independence is very important. So we need to first check whether there is preference independence. Okay, so suppose we have two attributes x1 and x2. Okay, we can say x1 and x2 is preferentially independent of the third attribute x3. If you say x1, x2, x3 and x1 dash, x2 dash, x3, the outcome of that does not depend on x3 at all, right? Then you say that x1 and x2 are preferentially independent of x3, right? So for example, if you take noise, cost and deaths, then you can say noise and cost are preferentially independent of deaths. So suppose we prefer a state with 20,000 people residing in the flight path and a construction cost of 4 billion over a state with 70,000 people residing and a cost of 3.7 billion when the safety level is 0.06 deaths per million passengers miles in both cases. And we would have the same preference when the safety level is 0.12 or 0.03. And the same independence would hold for preferences between any two pairs of values. Okay, so in other words, you are saying cost and depth are preferentially independent of noise, and noise and depth are preferentially independent of cost, right? So we have three things here: cost, depth and noise, and we can say that all these, if you take any two of these, they are preferentially independent of the third one. Then you say that you have mutual preferential independence basically, which is called MPI. So if you have mutual preferential independence, then it makes it easier to work on these things because the attributes are independent of each other. Okay, they are not dependent on each other. Okay. So if you have the attributes x1 to xn which are MPI or mutually preferentially independent, then the preference behavior can be described as maximizing the function. So this is a value function V, which will be sigma Vi into xi, where each Vi is a value function referring only to the attribute x1. Okay. So suppose you have V of you have three variables, x1 is noise, x2 is cost, x3 is deaths. So we can say it's something like saying V1 into noise, that is some constant into noise, and some constant into cost and some constant into deaths. So you may get a function like this. Okay. So this is called a additive value function. Okay. So what you can do is you can sort of add them together, right? So that is one thing. So what they say is even when it doesn't strictly hold, okay, you can use an additive function as a good approximation to the agent's preferences. So that's a possibility, that's a way of going about this problem basically. So you can also talk about the utility independence. Okay. So we spoke about preference independence. So you can talk about utility independence. A set of attribute X is utility independent of a set of attributes Y if preferences between lotteries on the attributes in X are independent of the particular values of the attribute in Y. And you can also have mutually utility independent. Okay, just like we had earlier, mutually preferentially independent. So we could say that in the case of the airport attributes, they are also mutually utility independent. Okay. So if that is the case, then again you can get a utility function in this way. So we can put the utility function as some constant k1 into utility of u1 plus some constant k2 utility of u2. If you are talking only of three variables, K3 and utility of K3 plus etc. Right. So you are getting various combination of these utility. So here basically you have three constants and you have three utilities basically in this, right? And that is used to get the overall utility basically. Okay, so let us look at what is a decision network. So till now we have seen the Bayesian network. So how do we get a decision network from the Bayesian network? So the decision network actually combines the Bayesian network with the additional nodes for actions and utilities, okay, so that you can make a decision, okay, so that's what we are, so we will use the airport sighting or finding a site for the airport, okay. So a decision network represents information about the agent's current states, its possible actions, and the state that will result from the agent's action and the utility of that state, okay. So let us see what are the various types of nodes that you have in a decision network. First of all, you have the chance nodes which represent the random variables just like we had in the Bayesian belief network, right. So the things that come into the chance nodes are things like construction cost, air traffic, the potential for litigation, deaths, noise, cost, all these variables will be the chance nodes that you are going to use here. And the second one is what is called the decision nodes. What is the decision node? It's the node which makes a decision on the choice of action. In other words, in this case, which is the site to be chosen, right? So you may have say three potential sites. So out of these potential sites, which is the one that you are going to choose? So that is the decision node. In this case, the airport site action will take on a different value for each site. The choice influences the cost, safety and noise that will result. Then third one is the utility nodes. The utility nodes represent the agent's utility function. So it will give the utility function for the different sites that you are going to check out, right? And that will help you to decide what is the site that you are going to actually use. Sometimes, so we can see here that we have the decision network here where we have the chance nodes, these elliptical things are the chance nodes, and we have the rectangle here which gives the decision node, and this is the utility node that we have, okay. So the airport site is actually the airport site chosen is influenced by deaths, noise, cost, all these three variables, right? And we get the utility node here which will decide which site is to be chosen basically. And this gives a simplified version where the outcome nodes like deaths, noise and cost are left out. Okay, so you just have these values. So this is a simple method of putting the same thing, right? So this is the what is known as the action utility representation. Okay, how do we evaluate the decision networks? Okay, so what you do is you have to choose the actions by evaluating the decision network and choose which action to be taken. In this case, which site is to be chosen. So for each possible setting of the decision node, you have to see what is the utility you are going to get, and the utility node, which is the diamond which is over there, will decide okay, which is to be chosen. So once you set the decision node, it behaves like a chance node, okay, and it behaves like a Bayesian network basically. So first you set the evidence variables for the current state. And for each possible value of the decision node, you set the decision node to that value calculate the posterior probabilities for the parent nodes of the utility node, okay, using a standard probabilistic inference algorithm, and calculate the resulting utility, and the one which gives the highest utility, that is the action which you are going to return. So that's how this decision network basically works. Okay, next we talk about what do you mean by value of information, right? Um, when the agent has to make a decision, okay, we assume that it has all the information that it wants, right? But it's also possible that an important part of decision making is knowing what questions to ask. Okay, for example, a doctor cannot be given all the results of all possible tests, right? So he has to decide what question to ask, what tests to be done, etc. Okay, because some may be expensive, some tests may be hazardous, and you cannot do all tests, right? So we talk about the information value theory. In other words, the value that we set on information. So we are talking about that. So the value of any particular observation must derive from the potential to affect the agent's eventual physical action. So if it affects the action of the agent, the value of that information depends on that basically. Okay. So how do we get the formula for the value of information? So what we want to do is we need to find the value of perfect information, right? So suppose we know that expected utility of some action alpha given E is the max of P result of A equal to S dash given A and D into U of S dash, right? So this is the expected utility. Now this is the expected utility with evidence E, but now suppose you have a new evidence EJ, right? Then you can put EU or expected utility as using the new evidence EJ, right? You will get, if you do the same thing with along with the new evidence EJ, okay, you get a new expected utility. And the difference between these two will give you the value of perfect information, okay. So EJ is a random variable whose value is currently unknown. So to determine the value of discovering EJ, we use a current belief about its value. So value VPI of EJ of the new evidence EJ is equal to sigma probability of EJ is equal to, so it's taking the probability of the evidence giving the evidence E and the difference between the expected utility and the expected utility of using EJK or EJ and the expected utility without using it. Okay, so this is called the value of perfect information. So what happens is when you are using, if you suppose you had utilities U1 and U2, two utilities which you are getting, and when you use the EJ you may get U1 dash and U2 dash, okay. So it's something like saying, suppose you have two routes A1 and A2, okay, through a mountain range, and A1 is a nice straightforward straight highway, okay, and A2 is a winding dirt road. So obviously A1 will be preferred over A2 unless it is blocked by avalanches, right? Whereas it is unlikely that anything blocks A1. So U1 is definitely higher than U2. But you can also obtain some satellite reports EJ on the actual state of each of the roads that would give new expectations U1 dash and U2 dash. Okay. Now, so you need to see whether it is worth the expense of getting the satellite report or not. Okay. So what happens is that it may not have value in most cases, but suppose you are carrying a seriously injured passenger and you are choosing between two different winding dirt roads, right? So obviously you would like to find the one which is better, okay, which has higher utility. Okay, so for that you can use your satellite reports. And if you use a satellite report and you find that one of them is blocked and you have to take the other one, then you find that the information has value. Okay. So here, if you take these three cases here, okay, this is a you find U1 and U2 are the two utilities, and you find A1 will almost certainly remain superior to A2. So the information may not be needed. Whereas here, even though your A choice A1 is better than choice A2, it's possible that the choice may be unclear, right? Whereas here you find in C also the choice is unclear because you find that the peak is different, right? So the fact that U2 has a higher peak means that its expected value is known with higher certainty than U1, right? So there is some ambiguity there. So when there is ambiguity, it makes sense to use the extra information, but it may not make sense in these cases. That's the basic idea. So if you want to summarize this, you can say information has value to the extent that it is likely to cause a change in plan. So only if it's likely that it may cause a change in plan, only then the information has value. And in such a case, the new plan may become better than the old plan which we are talking about. Okay, so we'll stop here and we'll talk about the value of little bit more about the properties of value of information and about a information gathering agent, and then we'll go on to complex decisions in the next session.